So now we've seen that if we define our global features f as a sum of local features g, we can efficiently calculate this function from sentences to tag sequences using the Viterbi algorithm. That is critical for two reasons. One is, if we want to apply our global linear model to a new test sentence, we clearly need to calculate this function f. And we need to be able to calculate it efficiently. Secondly, if we think about the perceptron algorithm, the main computational step in the perceptron algorithm is at each training example to find the highest scoring tag sequence under the current parameter settings. And so it is going to repeatedly calculate this argmax. And again, it's therefore critical that we can do this efficiently. So let me just talk briefly about how the perceptron works for these types of models. So again, here is a recap of the perceptron algorithm. We have inputs xi, yi for I equals 1 to n. In the tagging case, these will be sentences paired with entire tag sequences. We set v equal to 0. We define fx to be this argmax, where we iterate over all members of gen, score each member, find the highest scoring structure. And then in the actual parameter estimation step, we take big T passes over the data. We go over the examples one by one, so we have I equals 1 to n. And this is the critical step. So at each point, we find the highest scoring tag sequence under the current model. If it's not correct, we make some update to the parameters. So in the tagging case, this algorithm looks like the following. We have a training set of training examples consisting of word sequences paired with tag sequences. We've used n sub I to be the length of the ith example here, or the ith sentence and the ith tag sequence. We initially set all the parameters v to be equal to 0. And again, I'm going to take big T iterations over the training set. I visit the examples one by one, so I take I equals 1 to n. I'm iterating over the training examples. The first thing I do is I calculate the highest scoring tag sequence under this score, v.f, and we're going to assume that f is equal to a sum over these local feature vectors. And that means that critically we can calculate this highest scoring tag sequence under the current parameters using dynamic programming, using the Viterbi algorithm. If the output from our model Z is not equal to our target output T, so if there are one or more tag errors in this sequence we proposed, then we do this very simple update again. We say v equals v plus f minus f, where this f looks at the correct tag sequence and this f looks at the incorrect tag sequence. So again, at a high level, the critical thing is we've leveraged this kind of definition of f, that is a sum of local feature vectors, in the sense that we can now use dynamic programming to find the highest scoring tag sequence for each training example under the current parameters. And then we use the standard perceptron updates. So here are some results from the perceptron on a couple of data sets, comparing it to a log linear tagger. This is first part-of-speech tagging data, and you can see that the error rate for the perceptron is very competitive, actually slightly lower than the result for a log linear tagger. And secondly, we have the problem of noun phrase chunking. So this is actually the problem of taking a sentence as input and recovering noun phrase boundaries, where I only look at noun phrases which are non-recursive. So these very low-level noun phrases like the dog or the cat. So this is a segmentation problem in the same way that named entity recognition is a segmentation problem. And it can be treated as a tagging problem, the same way that named entity recognition could be treated as a tagging problem. So in noun phrase chunking, again, we see similar levels of accuracy, but perhaps slightly higher accuracy for the perceptron. So the perceptron is certainly a competitive algorithm in this particular domain in tagging problems. It offers a very interesting alternative to log linear taggers. It's a simple algorithm, and it's really rather simple to implement. And perhaps most importantly, this way of thinking about global linear models, where gen is exponential in size, but f is defined through some sum of local feature vectors, we'll see that this is a very powerful idea. Tagging was one of the first problems which was addressed using this kind of technique, but in the next segment of this class we'll look at dependency parsing, which is another application of this technique, and where this idea of decomposing f as a sum of g's has really been employed very effectively.